Welcome to the Segmentation, Classification, and Machine Learning session. Good job finding the room in the mezzanine here. My name is Jeff Lidke. This is my colleague, Han Hu. We're on the Raster team at Esri, and we're going to be presenting the classification tools and capabilities in Pro. So how many of you use ArcGIS Pro? Okay. How many of you have used any of the classification tools in ArcGIS Pro? A few people. How many of you have used classification in other packages? Okay, so pretty knowledgeable audience. These are the things we're going to cover. Overview of the classification workflow in Pro and the tools available in Image Analyst. And then we're going to talk about some of the capabilities and workflows in the classification wizard, segmentation, and then we're going to introduce deep learning, which is a interesting capability that we're working on, and you'll be interested to see those results. The classification tools are in a new extension called Image Analyst. It was just introduced, and Image Analyst is designed for image analysts, believe it or not, and it's mostly for working with imagery rather than rasters per se. So it's imagery focused. The capabilities include full motion video, where you can play video in a video player and see the footprint of the video and the ground track of the sensor, etc., on the ground. And you can compile features in the video, and those go from image space into map space. So you see those features being drawn on the ground. You can display GIS information on the video. Stereo compilation is also supported in Image Analyst. There's 200 math tools and functions for putting together your own algorithms and deploying those either in Pro or in Raster Analytics in GIS Enterprise, ArcGIS Enterprise. And then there's also viewing and working with oblique imagery. So classification is part of that as well. So talking about the classification workflow, the first step if you're going to be doing object-oriented image analysis is segmenting your image. And we're going to talk in some detail about that. Segmentation is combining similar adjacent pixels into objects, and then those objects are representative of features on the ground and classified. The next step is training. So this would be collecting training samples to train your classifier, and then actually training the classifier with one of these classification approaches. And we'll talk about those in some detail. So the result of training the classifier is an ECD, an Esri classification definition file that goes into the classification tool and produces your class map. Once you have your class map, then you assess your accuracy of that class map. And if there's any issues, then you would go back and adjust your training in an iterative fashion. And once you're satisfied with your accuracy assessment, then you have your final class map. Class map is a thematic map, a categorical map with attributes. It's a raster. So classification, GP tools, geoprocessing tools, you can see them all. There's many. They cover the whole workflow from defining your segmented image, collecting your training, training your classifier, and then classifying your result. and then accuracy assessment. This is classification on the imagery tab on the main toolbar. So on the main toolbar is an imagery tab. It contains the wizard and the classification tools and the classification group. It's contextual. So once you load an image, then these are enabled. The classification wizard is a guided workflow that guides you through each step of the classification process. I should go back and explain the classification tools. These are commonly used functional categories, segmentation of your imagery, the training sample manager, where you collect training and manage your training sets, and then classification itself. This is what the wizard looks like. So it covers the 8 functional areas of classification, as you can see there. First, you configure your project, then you do segmentation, training sets, training the classifier, etc. You can see that there. We'll look at this in some detail. So these tools are available across the platform. So you can do classification in Pro. You can do it using raster functions. Raster functions is dynamic processing on your display. So if you want to do some testing, you can look at your classification, see if it's acceptable. If it isn't, go back, adjust your training without processing your image and storing that image on disk. And then these tools are also supported in Enterprise, configured for Raster Analytics. This is distributed processing, and it's through Pro, through the portal, and in your Enterprise system, it's configured for any number of servers that are dedicated to processing the image and storing the image. So you can take advantage of the cloud in that distributed environment. So what is segmentation? You've probably heard the term object-based image analysis. This is where, as I mentioned, adjacent pixels having similar spectral characteristics are grouped into segments or objects. They're treated as superpixels by the classifier, so the classifier is classifying these objects, these segments, as opposed to pixels. I should mention that pixel classification is supported too, in the same exact workflow. So the objects are classified according to their spectral and spatial characteristics, and that's one of the prime advantages. So rather than relying only on the spectral information, you can also bring in spatial information. So a size of an object, the shape of the object, proximity to similar objects or dissimilar objects. So your classification accuracies are improved from, spectral classification is often 60, 70%, maybe 80 if you're really, really good. But when you bring in that spatial component, it's common to achieve high 80s and into the 90% accuracies using that spatial information as well. The other advantage is those objects represent real features on the ground. So you're not going to go in and manage some pixel differently than its surrounding pixels, even if it's classified differently. But the objects represent real features that you can identify. It's a building, it's a sidewalk, it's a street, it's vegetation, whatever. So this is a Worldview 3 scene, 50 centimeter, and once we've done segmentation, you can see, see what it's doing. It's grouping, say, the area in the airport tarmac has a lot of variability in it, but it is the same feature, right? So even though spectrally it looks different, it's treated as an object. Same with some of the vegetation you can see. So this is the classification workflow. It could be divided up into 5 functional areas. So we're going to talk about each one of these. You perform your segmentation, then your training, you train the classifier, classify the image, and then assess accuracy. So image segmentation. The inputs into this function is a 3-band 8-bit raster. You want this 3-band raster you want to choose your bands to differentiate your features of interest. You don't necessarily want it to be a pretty image at all. You want to be able to see the features that you want to extract from the image, and those features will, or that WYSIWYG, what you see is what you get, that's what's going to be driving that segmentation. That's a good rule of thumb. You can add other image information later, but for the segmentation piece itself, it's 3-band, 8-bit. You can use raster functions to test the parameters. So once you have fine-tuned and optimized those parameters, then you can process the imagery to disk. It's compute intensive. So it's one of the capabilities that can be performed in the Raster Analytics environment. And let me show you a little bit about the parameters. I don't know if you can see, but I'm using a raster function here. And this is a scene that has been segmented using a lot of smoothing. So you can see that the detail in the roof here has not been segmented out. The parking lots are segmented, but no cars are. So this is using a low spectral and low spatial detail parameter settings. If we choose different settings, the defaults work pretty well. I'm just going to leave the defaults, but it's between 0 and 20 in terms of spectral and spatial detail. And then this minimum segment size in pixels, that's related to your minimum mapping unit. So the minimum size that you're trying to get. If you're trying to digitize sidewalks, you want a pretty small number if you're using satellite imagery. And you can ask for just the segment boundaries or segment the image itself. I'm going to ask for the boundaries. So it'll take a couple seconds there. Now, using the higher detail, you can see that it's segmented a lot more of the detail on the roof, the cars, etc. So this is how, and so I can roam and zoom this image because it's a raster function that I'm using. So it's processing these on the fly. So the idea here is that you would optimize your parameters and then process the imagery to disk. One other thing I just wanted to touch real quick on is when I put these in, and I said, go ahead and process that. There was an option here. Create a web image layer or a new raster layer. It loaded the new raster layer here in my contents pane. But if I choose the web image layer, that's what kicks the process off to enterprise and in your distributed processing environment. So by choosing where it gets processed, you can control where the segmentation takes place. So that's segmentation. The next step is training. Oh no. Training samples management. Great. Thank you. Okay, so collecting training, you can collect training using the methods we talked about. You collect polygons that represent the classes that you're trying to classify your image into. That can be labor intensive, but you are in control of that, so it's a good technique. You can also generate training automatically by using existing information. So if you have an existing class map that's accurate and you know the accuracy of that, you can use that to generate your training. It will, you give it a schema and it will select those classes according to that schema and however many samples you want per class based on that class map. You can inspect those training samples by doing a cross-validation. So it takes some of the training, trains and classifies your image, and then compares it to the other training that it hasn't used, that's used as reference. So it uses part of your training samples as reference and then does a cross-validation to get an accuracy assessment of that. That will allow you to fine-tune your training before you actually classify your image. So that's helpful. Then you train the classifier. The machine learning classifiers are support vector machine, random trees, which is random forest, and deep learning, which we'll talk about later. Also support maximum likelihood and isocluster for unsupervised classification. The inputs include the segmented data set and an additional raster data set. This is where you can really add information that influences your classifier with the second raster data set. So if you want to differentiate an asphalt roof from an asphalt road, you can add LiDAR data, for example. So if you have, if you subtract your DTM, your ground, from your DSM, your surface, then what you're left with is height of features above the ground. Include that in this raster. If you're interested in vegetation, put an NDVI layer in there. So you can put GIS information in here as well, as long as it's a raster data set. So this is a stack of rasters that will be considered by these machine learning algorithms. The advantage of these is that They don't have to be a normal distribution of pixels or segments, and you can have a low number. You don't need to have a statistically significant number such as 30 or 50 samples per class. That can be quite tedious sometimes. And when it considers these layers, if a layer is not adding to the classification, it just won't use it. So then, of course, you add your training samples and your segment attributes if you're using a segmented image, and those include chromaticity, color, the mean value of the object, and the standard deviation, as well as some of these spatial characteristics. So compactness, rectangularity, and the size. And then that outputs an Esri classifier definition file, which includes all of the definitions for the classifier that you chose. Next step is you classify the image using all those inputs that we just talked about, and then assess the accuracy. So if you have ground reference, your class map will be compared to that reference and give you producer and user error matrix and a kappa score. Are there any questions up front? And I'm going to jump into a demo after that. Okay. So this is the classification wizard. It guides us through the various steps, as I mentioned. So when we do the project setup, I've specified we're going to do supervised classification, other choices unsupervised, of course, object-based or pixel-based, your schema. If you don't have a schema, we give you a default schema that's easy to modify. And then other inputs such as, is it going to be a segmented image? Are you going to do object-oriented classification, your training samples, and your reference data set? So then it jumps to the next step. It skipped this. So these colored dots up here show you where you are in the classification workflow. It skipped the second one because that's the segmentation. I already segmented an image, so we're skipping that step. These are the classes in the schema, and we could add a class, and these are the actual training samples down here. And one thing that's very, very handy is we can select training sets based on the segment itself. So rather than collecting a polygon, we can collect a segment. So here's turf. And let me show you an example of that. You select the segmented image, and now you can go in here and collect your training as a segment. So rather than digitizing every node, and it's kind of the excruciating part of image classification is collecting the samples. This is almost fun, right? You can just quickly collect. This is such a time saver. And the other good thing is those are some turf. Let me collect a building top. Say gray roof. See, I selected this gray roof. I didn't have to worry about all this stuff on top, air conditioning and other things on top of this roof. It's already excluded from this sample. So collecting good pure samples is pretty easy using this technique. Okay, so there's our samples. Next step, training the classifier. Let's use random trees. We can specify 100 trees with 50 branches and choose our attributes that we want to classify on. Standard deviation is a good one, sort of related to texture, variability within the sample, and rectangularity. So that'll take a minute or so to run. And while we wait for that, I'll show you just a few more nice features of collecting training samples. So if we wanted to add another class, it's easy to do. These parent classes, pervious and impervious, contain these sub-classes. So we could add another subclass to pervious if we want, and call it almond trees, and give it a value, give it a color. And voila, it's part of this parent class. If we want a completely new parent class, we can do that as well. There it is there. So pretty easy, pretty handy. One thing we're working on, and I'm not really supposed to talk about stuff we don't have yet, but we're going to be able to ingest well-known classification schemes. So say Anderson 1, 2, I'm sorry, I forgot, but there's some well-known international classification schemes that, or you can develop your own classification schemes, save those, share those across your organization. So, see how our classification is doing. It has loaded it here in the contents pane. It's called Preview Classified Image because it gives you a first assessment of your results. And if you like those results, you can go ahead and say, good, classify the image. If not, at this point, you can go back into your training set and adjust your training accordingly. One other thing to discuss briefly is the segmentation parameters. It is a balance between the spectral and spatial detail. And as the detail goes down, the time to process goes up. You're doing a lot more computations, a lot more smoothing. So there's some rules of thumb. The the defaults of 15 and 15 are pretty good. You can get a lot of detail, but not too much detail in your segmentation with those defaults. But you may be interested in different types of features, smaller features or other feature types. So you can see as the spatial detail goes down and the spectral detail goes up, there's kind of a sweet spot in this corner here and this corner here. Yes?
Spatial detail, though, a smaller number is higher on your graph here?
Yes.
Yeah, smaller number.
Right. And the code for this is parallelized, so you can run segmentation on your desktop, on multiple processors, or in the cloud. It's designed for distributed processing. Okay, so we're getting there on the classification. Any other questions in the meantime? Yes, sir?
We used this a couple of weeks ago in agricultural crop imagery.
Okay.
Do you have any recommendations for minimum mapping unit for plants and 10-inch resolution? Isn't it still just going to be one? And that's when we're trying to classify weeds versus crop, for example.
Generally speaking, yes, but it depends on your crop and the space between rows and whether it's orchard or whatever. But a low minimum mapping unit is really just fine because in your classification, you're just going to be combining those segments. So.
With the way the weeds manifest with the crop, like if they're patchy or is that going to dictate sort of some of the parameters you might adjust?
Yes. So if they're elongated, so if they're thin but long, you would want a smaller mapping unit to accommodate the thinness, the width. Yeah. Same with sidewalks or any long linear features. Okay, looks like it classified. So now I can merge classes if I want to into their parent class, for example, impervious. But this is for the accuracy assessment, and I'm going to go ahead and assess the accuracy of the land use, which will not be as high as the accuracy for pervious impervious, because you can misclassify some of these, but they're still pervious, right? So even if you if you call an asphalt roof a road on a land use map, that's incorrect, but for pervious impervious, it's correct. So let's see how we do here. Okay, so we'll compute the accuracy assessment. Here are the results. And I should mention that I just did a stratified random sampling. We can do an equalized stratified random. So stratified random, you can see here, is randomly distributed points for each class where the number of points is proportional to the size of the class. Equalized is the number of points are the same for every class. So it's still randomized, but you're collecting 50 points for every single class rather than 20 points for a smaller class and 100 points for a larger class. So cap of 0.9 is pretty decent. That's very good, actually. I'm surprised. I love when this happens. So let me leave this just for a moment. And I had set up let's go see what we get if we just go with impervious pervious. And let's do equalized. Although we want to compare the same, but that's okay. We'll do equalized. Here's our error matrix, and yeah, 0.96. So even though, so let's look at the other one. We can look at it in detail. Yes?
What are you basing your accuracy system on? Is there some separate ground truth?
Yes.
Can you repeat the question?
So the question is, what are we basing the accuracy on? Is there some ground truth or ground reference? And the answer is yes, there is ground truth. What we did is went into the imagery and selected polygons that we knew the identity to, and then compared to those. And that is this. So each class is in this error matrix, and this is the diagonal here, where class 22 is compared to class 22, and you should have your higher numbers along that diagonal. What this is showing, though, is that for this particular class, C25, so the user and producer, it's 255 were correctly classified, but 25 were not. They were classified as C22. So I don't know exactly what the identities of these are, but I'm guessing that that probably was gray roof and asphalt, something like that. There was some confusion there. So go to next, and now we're computing the result, the final class map. And here we can make any corrections to the final class map before it's written. Okay, so here in this canal, it got classified, water got classified as shadow. So I can reclassify a region from shadow to water. And this is basically just editing at this point. And then once we've done that, you say run, and it incorporates those edits into your final class map. And
treat it as a training set, or they're just making that one modification?
just making the specific modifications that you've specified. You're painting pixels.
Fast.
Yeah, yeah, it generates it real fast. So it's only changing what you've done, yeah. So that's a demo of the workflow through using the wizard. And as you can see, it guides you through, and it's designed for production. But again, you have all the GP tools, and you can do this outside of the wizard if you have special parameters or special feature space that you're trying to classify. So any questions off the bat, or I'd like to introduce Han, and he can give you a synopsis of what's going on with the deep learning. Right? Yes?
Is the schema created automatically when you do segmentation? How does the schema get created?
The schema is created interactively. So when you start your training, a default schema is loaded, and you can navigate to your directory and use your own schema, or you can use the default schema and edit that schema. The default schema is Anderson 1. But you can edit that.
And is there a way to recreate your own schema and then just use it?
And use it over and over. Yeah, you can save your schema. You can mod it. You can save it, reuse it, edit it, save it as another schema.
No, but create it before you run segmentation. Is there a way to create a schema before you run segmentation to say, well, these are the items that I would like the image to be classified by? And then...
No. No, the schema is unrelated to the segmentation. So when you do segmentation, really the key and the trick is to be able to visually discriminate what you're interested in. If you can see what you want, it'll segment it. Okay. Here, I'll just clip it on.
Thank you, Jeff. Good afternoon. My name is Han. I'm a software engineer in the Raster and the imagery team at Esri. So what I focus on is the deep learning part. I develop products which uses deep learning technology to solve the different problems on aerial or satellite imagery. So today I will give a short description or introduction on deep learning and see how deep learning technology can solve the image segmentation or land classification problem. So deep learning is getting very, very popular, and everyone is talking about deep learning, and it's used in a lot of applications, like autonomous drivings, autonomous vehicles to segment the roads, buildings, and trees. So there is a lot of application, and researchers, they are doing a lot of work to see how deep learning can segment the satellite imagery using those technologies in computer vision industry. So deep learning is not a brand new technology. It has been there for many years, and it's getting popular only recently because there are two factors. That's what I understand. So the first factor is that we are getting a lot more data set, training set than ever before. So we have a lot of data set, then we can train a better model to get a better performance. And the second factor is that the device, because deep learning, usually a deep learning model has tens of thousands parameters to fine tune, to train. So and it requires a lot of computation power. And nowadays we have like NVIDIA, we have powerful GPUs, and to train a model in a very short period of time. So that's why the deep learning model now gets a lot of attention only from recent years. So it's a subset. The deep learning is a subset of machine learning. So only the difference between the typical traditional machine learning and deep learning is that the deep learning use the concept of layers, and you can put a lot of layers. So layers to do some task. So the layers, you can think it as a function. It's a function which operates on the previous result from the previous layer. And your first layer is what your input. And in our case, is satellite imagery. And your output, your final output, which is the final layer of the deep learning, is your segmentation result, right? So you can put a lot of layers, and that layers, you can design your own models. And the models the layer can be very wide, and it has a lot of parameters to learn, and it can also be very deep. So you can, and the layers nowadays on imagery, the layers we use most often is convolutional layers, fully collected layers. That's most used for imagery. So you can think it as a function, as a black function, but the parameters are unknown. The parameters need to be learned by given some ground truth. And the ground truth is a pair of, has two parts. The first part is your input, and the second part is the output, which is a segment, is a classified map. Your input is your imagery. What I will talk about here is totally an introduction. It's not ready, the functionality is not ready in ArcGIS Pro yet. So we did some, we are still in a research stage to see how the deep learning can improve this, or can be used in the land classification problems. So we did some project with our partner, NOAA, and they gave us their a very good data set. And the data set includes two parts. One is the imagery they use is the lame imagery, which has a 1 meter resolution, and the second part is they labeled each pixel into 6 classes, and it's very accurate, this data set. The 6 classes has forest, shrub, bareland, impervious surface, open water, and grassland. So every pixel is labeled. And this region is very large. It has 2,000, it has about 2,250 square miles, and it has billions of labeled pixels. So what we did, we trained a deep learning model. So first step is, because the deep learning model cannot work on that large area. So we need to divide this region into small training samples. So we use a GP tool. This GP tool is already in the release, in the current release. It's called Export Training Data for Deep Learning. So we use this GP tool to divide the training data set into small samples. And each small sample is 572 pixels wide in both width and height. So, and we feed the samples into the training process. And from the input is a 572 pixels wide image sample, and the output is corresponding classified map. So we build a neural network, a deep neural network, and it's used very common in segmenting medical image. This neural network architecture, it does a very good job in segmenting the medical images. And we use that model. the same architecture here in the remote sensing industry. And we trade this network, and we come up with we end up with a deep learning model. So the deep learning model can learn the pattern, what a grass looks like, and what a land looks like, what a lake looks like. So it learns all the parameters itself by iterating, fine-tune the parameters until getting the best accuracy using the ground truth data. So we have evaluated the approach. We use the trade model on some validation set, which already has a ground truth, but is not included. But that validation set is not included in the training set. So we evaluated our model, and the overall accuracy is very promising. It shows 92% correct using deep learning technology. So what this means is only 8% of the pixels is misclassified, and the model is used in a totally new area, which the training is, that area is not included in the training stage. So this, what we have found here in Esri is the deep learning technology is really a very promising direction to go. And we are actively developing and researching every possibility to incorporate the deep learning method into ArcGIS Pro. Then everybody, but it's not there yet. We just to convey a message that we are working on the deep learning part. If it proves that the deep learning part can be a beneficial, great benefit for remote sensing imagery or satellite imagery, so we will try to make this component into ArcGIS. So still stay tuned for the future release and see what we can do on the deep learning part. Yeah, that's all. That's all I want to say about the deep learning part. So, is there any questions you guys want to ask?
What release are we looking at?
I cannot guarantee that what release we are going to make this available, but we are making a great effort in making that available. So we are trying to release that as soon as possible. But it requires a lot of work because first right now we are only in a research stage. We are trying to prove the concept that the deep learning can do the job. And the next is the product design. We want to design the product, how people can use that to make it convenient, to make the workflow convenient and easy to use. So I cannot guarantee which release we are going to do that, but yeah, we are working on that.
Is there any area limitation, like what's the area that you can apply this to?
So
Can you repeat the question?
Oh, the question is there any area limitation on this approach? So what area we can use the approach on? So because deep learning really requires where you train the model, where you can use the model. If you train because different geography locations has their own maybe spectrum properties. So the deep learning part can only learn the pattern in that region. If you use the same model in a different region, then maybe very possibly the deep learning model cannot work very well. Say we have another demo. We trained a roof detection model on Las Vegas, and then we use a roof detection on New York. Then it proves that the model doesn't work. So we can only use a model where we trade on the same region.
Is that with the same satellite sensor?
It's the same satellite sensor, but since the roof has different shapes and characteristics, so the model doesn't have the knowledge to know what's the roof or what's not the roof.
Just to follow on that question, if you have the model that you use different satellite sensors, one year you use one sensor, and another year you use another sensor, will it still work?
The question is if we use different sensors, will this still work? The answer is no. So you need to use, because the machine doesn't have the knowledge, you need to feed the machine the knowledge. The machine can only know the pattern you teach the machine to do. So if you use different sensors, say you try a model in RGB, then you have another sensor only have an infrared. Probably it only has the knowledge to how to recognize some object or how to classify on RGB band, but it doesn't have the knowledge to classify the same thing on the infrared.
But if the spectral characteristics are similar, then you could. For example, worldview 2 and worldview 3 have very similar spectral characteristics, then yes, it would.
What do you think of the accuracy performance in terms of classification scheme of level 1 or level 2 or coming to level 3?
What's your question again? I'm sorry.
What do you think of the accuracy performance
Mm-hmm.
and even the classification level? You did it at level 1, 6 clauses.
Mm-hmm.
Yeah.
What about the level 2, which is maybe 12 clauses, or level 3, maybe more? So when you have more clauses of communication,
Okay.
what do you think is the accuracy performance?
So I think once you have more classes, the model gets more complicated, right? Because it needs to learn to distinguish more classes between each other. So I would think if you do more classes, the accuracy would decrease a little bit, but we don't have the numbers for that.
What about performance?
The,
Much longer?
the performance is the same. The speed is the same. It's just the accuracy performance. It might be different if you have detailed classification schema.
Yes.
So do you see this eventually being more accurate in the end versus a manual classification effort?
So,
Can you repeat the question?
so the question is, do we see any better performance like than the SVM or random forest from compared with deep learning, right? We see the overall accuracy is better than the traditional method, but we also found some drawbacks from deep learning. This model actually favors the major classes. Like here, we have 80% of the area is forest. So if the classifier just blindly guess every pixel is forest, the classifier is still 80% correct. So it's hard to say whether this is better or worse than the SVM or classifier. So this model, we found the deep learning model, this specific model architecture, it favors the major classes by sacrificing the accuracy in the minor classes like shrub. So maybe the shrub has a lot more errors than the grass, than the forest. So it's hard to say right now whether the deep learning is better than the SVM or random forest. But we are still like exploring every possibility that every new state-of-the-art technology to be applied here. So that's just a short introduction in the project that we did recently.
Han, can you talk a little bit about the training? It's highly dependent on the training, and the training has to be voluminous. A lot of training samples are needed.
Yeah.
So can you talk a little bit about the training?
Yeah, also in order to make deep learning work better, the more samples you have, the better the result will be. So because deep learning, deep learning is used in autonomous vehicle to recognize person versus vehicles or road segments. So And usually deep learning requires a lot more samples in order to work better. So in this area, this region, we have 80,000 small samples to train the neural network, and we achieved this accuracy. But if you just have maybe a few hundreds of samples, it cannot do a very good job.
And there are consortiums now that are coming together to collect and share training samples. So Berkeley has started one. There's a few international ones. So it's just going to continue the database of samples of Earth features. And as that grows, then deep learning will become more and more accurate. Yes, ma'am?
So going with that concept of like, are you using publicly available training data, or are you creating it yourself? I heard one company, they had a staff of 30 people, it was an insurance company, and they worked, months and months and months with the staff to train like architects and such, figuring out roof lines, making sure that they had the gables done right, and I mean that's a huge project.
Yes. Yes.
And so that to me is like where, the limiting factor a lot in this is
So if you go to some AI startups in the startup zone, if you talk to them, you will find that most of the investment the startup is spent on the labeling. Yeah, so that's a limitation for the application. You need a lot of labor work in order to generate the training data set. Yeah.
So we recommend working with the consortiums to get their data. But I mean, Esri is set up for sharing data and being at least a repository for people to come to for that type of thing. Okay. Any other questions? Yes.
That enormous repository that you just described, the way you described it, is then unique to a specific sensor and is apparently not transferable to any other sensor, right? In this model.
Only sensors with similar,
Yeah, only sensors with similar spectrum properties or features.
And spatial.
And spatial, yeah. I'm not sure about how the spatial resolution can affect the performance, but we will need to do some experiments to see if there is some spatial difference, resolution difference, if they can work compatibly.
All right. Thank you very much.
Thank you
everyone.
for coming.